Today I'm going to do yet another exploration of high-dimensional spaces. This project was about simulating the same process, namely mitosis or cell division, in 2, 3, and 4-dimensional space, in order to hopefully get some better intuition for higher dimensional spaces and to see how the structures that form in each of the three cases differ from each other. And I also just wanted to know what would happen if we tried to grow a mini tumor in 4-dimensional space. How did I do this? Starting with a single particle, let's say in 2 dimensions, I create a small separation. Basically, I create 2 new particles very close to each other, and then I have a force law acting between them. And that force law causes the particles to repel when they are close together and attract when they are farther apart. So somewhere in the middle, there's kind of an equilibrium where there's zero force between the pair. At a given time frame of the simulation, a particle will feel a force vector directed towards each other particle in the system. And in order to move the particle or find where it's going to be in the next frame, we simply add up those forces, and that sum of forces gets translated directly into a displacement. So if you're familiar with particle simulations, you could realize that this is modeling a super viscous case. So in this simulation, the particles are not able to maintain any velocity from frame to frame. In other words, they don't have any inertia. So it's as if you have a bunch of particles that have forces between them, but they're moving in honey. So in the simulation, each particle represents a cell, and every 20 frames or so, I pick one uniformly at random, and we basically divide it in half. So we create 2 new particles that then get pushed apart by the force law. And this particular force law was very good at creating a evenly distributed, almost crystalline arrangement of the cells. And one way to quantify that regularity is to use this metric, which you could call local entropy. I learned about this idea by reading the paper on t-SNE. Basically, a particle's local entropy is going to be close to 1 if the distance to its k nearest neighbors is about equal for each neighbor. And it's going to be closer to 0 if it's really close to one of its neighbors but far from the other neighbors. So here I'm showing the 4-dimensional case where you just start the particles off in random locations and allow the force to aggregate them. And as they are kind of following into this lower energy configuration, you can see visually that the local entropy is approaching 1. And so from this we can tell that there's some kind of packing that's formed. Similar to the 3D case, you can think of some bubble tea balls at the bottom of the cup. Each one's kind of maintaining the same distance to each of its nearest neighbors. And so now I'm colorizing by the magnitude of the net force felt by each particle. And you can see how quickly they go into this lower energy state and find their equilibrium. It's so cool that you can literally watch the amount of force go to 0 as they're reaching their equilibrium. So in the following clips, I'm using Delaunay triangulation to put a network structure on our set of points, which kind of helps show the adjacency between points, which is definitely harder to see in 3 and 4 dimensions. So the last result I'm going to show has to do with measuring the volume to surface area ratio as we go into higher dimensions, because I noticed that the structures that formed tended to have a kind of spherical shape. To do this, the Delaunay triangulation gives us a set of simplices. For example, the tetrahedron you see here you need a minimum of 3 dimensions to truthfully represent that as a tetrahedron, and that's called a 3-simplex. And so our triangulation in the 3D case is built out of these little pyramids. Just like in the 2-dimensional case, it's built out of these triangles. And so I did this in MATLAB, and it's also possible to measure the facets which are on the exterior of the shape, or what's called the convex hull of the structure. And those facets will be a simplex of 1 dimension lower than the simplices that are composing the shape. So for example, in the 3D case, again, you have the structure built out of these pyramids, and then the facets, the surface is built out of these triangles. So in the 4-dimensional case, the facets that are on the exterior are actually built from these little tetrahedron. So what I've done is I've just simply calculated the ratio of the interior, or the total number of simplices composing the object, over the number of surface facets or surface simplices. So it's kind of like a very rough way of trying to compute like the volume to surface area ratio of this object. In 2 dimensions, you have a lot more interior triangles than you have lines on the perimeter. What's surprising is that as you move into higher dimensions, it seems to asymptote out pretty quickly to a ratio which is close to 1. So meaning that when you compute the convex hull, there's 1 facet simplex for every interior simplex, which kind of suggests that the entire thing is one giant shell, like it's all shell. I hope you enjoyed that. Goodbye.
Interpret.